Bandwidth for changelog is provided by Fastly. Learn more at fastly.com. Error monitoring is provided by Rollbar. Check them out at rollbar.com. And we're hosted on Linode servers. Head to linode.com/changelog. This episode is brought to you by Rollbar. Rollbar is real-time error monitoring, alerting, and analytics that helps you resolve production errors in minutes. And I talked with Paul Bigger, the founder of Circle CI, a trusted customer of Rollbar, and he says they don't deploy a service without installing Rollbar first. It's that crucial to them.
We operate at serious scale, and literally the first thing we do when we create a new service is we install Rollbar in it. Like we need to have that visibility, and without that visibility, it would be impossible to run at the scale we do, and certainly with the number of people that we have. Like we're a relatively small team operating a major service, and without the visibility that Rollbar gives us into our exceptions, it just wouldn't be possible.
All right, to start deploying with confidence, just like Paul and the team at Circle CI, head to rollbar.com/changelog. Once again, rollbar.com/changelog. All right, welcome back, everybody. This is the Changelog, and I'm your host, Adam Stacoviak. Today on the show, we're talking with Todd Gamblin, a computer scientist at Lawrence Livermore National Lab. And we got Moore's Law wrong on a recent episode of the Changelog, episode 267, as a matter of fact. And Todd hopped in Slack and said, hey guys, you got it wrong. We should talk about it. And that's what the show's about. We talked about Moore's Law, his work at Lawrence Livermore National Lab, the components of a microchip, supercomputers, and high-performance computing.
So Todd, we got Moore's Law a little bit wrong in our episode with Eric Norman. That was episode 267 about functional programming. And we were talking about Moore's Law, and I might have even mentioned on the show how lots of people get Moore's Law wrong, and then I got it wrong. So, embarrassed face is happening. But you were gracious enough to hop into our Slack, which is a place that we hang out and talk about our shows and programming topics and random things, blockchain mostly.
A lot of blockchain.
A lot of blockchain in there. And hop in our Slack community and straighten us out a bit about it and the particulars. And so we thought, well, if we need schooling, perhaps more people than just us need a little bit of schooling. So first of all, thanks for coming on the Changelog. And secondly, straighten us out on Moore's Law and what it actually is.
So I don't necessarily think that it was completely wrong on the show. Like the gist of what you guys said was fine. That, chips there's no more free lunch. You don't get free performance out of your chips anymore like you used to when the clock speed was going up rapidly.
Right.
But Moore's Law is not dead. Although, I mean, it's fair to be confused because there have been a lot of articles written about this. There was an article in the MIT Review that said Moore's Law is dead. Now what? But it predicted the death of Moore's Law, I think, out in the 2020s. And Intel CEO says Moore's Law is fine. The chips are going to continue to improve. So I think it's kind of hard to see what is really what's really happening in the processor landscape. So I mean, what Moore's Law actually says is that the number of transistors that you can cram on a chip doubles every 18 to 24 months. And so that's the part that is still relatively true, although it's slowing down. And I think, the interesting thing and the thing that people typically get confused with this is, so there's something else called Dennard scaling that broke down around 2006.
Okay.
And I think that's what has led to us having all these multi-core chips now, where, you got a lot of performance out of your single core chips before. And so what Dennard scaling says is that as your transistors get smaller, the voltage and current stay proportional to that. So effectively, your power density is the same for a smaller transistor than it is as it is for a larger one. So what that means is that you can basically jack up the frequency or the voltage on the chip as you scale the number of transistors, and so you get clock speed for free. over time. And
Just
so
by increasing the power.
yeah, that's just by increasing the frequency as you scale it down.
Mhm.
So the chips have effectively the same power for the area that you're putting all those transistors in, right? You want to keep the
Okay.
power envelope relatively constant because you're putting it in a device like, I don't know, well, these days like a phone,
Right.
or a desktop computer, and you don't want someone to have a really high power desktop machine that ramps up their power bill, right?
Right.
So you've got a fixed power envelope. You're increasing the number of transistors, and it used to be that you could also increase the clock speed. But because of the breakdown of Dennard scaling, you see that in like 2006, or around there, the chips are kind of capped out at like 2.5 gigahertz now, right? Like they're all sort of hovering around there. They get up to 3 sometimes, and then like you can find like 4 gigahertz monsters in like some of the bigger IBM like System Z systems. But effectively, it's kind of capped out there. I don't know if you remember, like I had 100 megahertz computers back in the day, or even I think my Apple II GS was like maybe kilohertz. I'm not even remembering, but
I don't think I go back quite that far.
Mm-mm.
yeah,
You might go back a little
No.
further than Adam and I in that regard.
I've always been in the megahertz.
I know that I was in the megahertz. I think it was like maybe my first was like 750 megahertz, somewhere around there.
Oh
That
wow!
would
So
have
you
been-
guys are picking up like
Yeah, that would have
late
been like
90s.
late 90s. Yep, exactly.
I do recall having
Yeah.
a 4 gig drive was my first computer, and then the second one I had a 20 gig drive.
Okay.
So I mean that's sort of like, don't relate it so much back to the chip, but mostly like how much space that I had to put stuff on,
Sure.
which sort of like relates to the chip era because it kind of goes in a similar scale.
Yeah, they go hand in hand. Yeah. So you got a little bit of seniority on us there, Todd. But nonetheless,
Slightly.
we've definitely seen the topping out. I mean, I'm on a what does it say, 2016 MacBook Pro, and I got a 3.1 gigahertz. So that's like 2.5, 3. Like you said, in the more server products, you might have 4 gigahertz. But that's what definitely has stopped.
Yeah, and the reason that that's broken down is that Dennard scaling ignores current leakage, and so as people packed all these transistors on the chip, you get something called a thermal runway, where you can't pack them that close without having a whole lot of power on the die. So you basically are capped at how much clock speed you can have. But what they do is you can still get these multi-core chips now, right? Like the number of cores on your chip has definitely been increasing. And so that's what they're using the transistors for, where they used to, pack more transistors into things like out of order execution and other stuff on the die. Now you're just building out and replicating chips of effectively the same size on the same, cores of effectively the same size on the chip. And so that's what your multi-core CPUs are doing. They're becoming their own little massively parallel machines.
So and back in that show, even then we were talking about the proliferation of cores, at least at the consumer level, hasn't gone crazy in terms of, you're still talking about 2-core, 4-core, 8-core.
Sure.
Probably from your purview inside the supercomputer labs, you can tell us about what machinery looks like inside there. But is that something that has also hit a threshold, or it's just slowed to where it doesn't make sense, maybe like you said, inside the same thermal envelope to have 32 cores on a laptop, for instance?
So I actually am not 100% clear on why they haven't, jacked up the number of cores on a laptop. I mean, I would assume that it's because people don't need that many cores that much, and also because most of the parallelism that you're going to want to do on a desktop machine is going to be on the GPU, and on like the phones, they have a lot of specialized hardware for things like video processing and like all these like AI units and things like that, which is interesting and has a lot to do with like, the eventual death of Moore's law too. But yeah, on the supercomputers, I mean, we buy the same, effectively the same chips, at least for some of the machines as your desktop machines. So like our commodity clusters, as we call them, they're Linux boxes with Intel and maybe AMD chips, and we're seeing a large increase in on-node parallelism. So like where we might not have more cores per per chip than what your desktop would have. We have a lot of sockets in the machines, and so the amount of on-node parallelism that's there is pretty high, and we try to use all that.
So where do you see this all going in terms of Moore's law? Like you said that it would be dying in 2020s. We're getting near that range.
Close.
What's your prognosticate out for us? What's it look like in the next 5 years?
So I mean, I think next 5 years, I think you'll see the rate of transistors that get packed on the chip start to slow down. I think currently the number of transistors on the chip is doubling at, I think, 2x every 3 years instead of every 1.5. So it is slowing. And then once that goes away, you're going to have to figure out how to take advantage of or how to increase your speed other ways. And so what that means in the hardware universe is I think you'll start to see a lot more specialized hardware. You're kind of already seeing that, right? Like we were talking about on the mobiles, you've got like the iPhone 10 has this like bionic processor or whatever it is.
Right.
You've got like custom GPUs and things. I mean, a lot of the processing that happens on your phone is just offloaded, and most of that is for like power consumption because you can do it a lot more efficiently in hardware. I think you're going to see like HPC sites start to shift towards, different architectures that can, make use of the same number of transistors more effectively for their particular workload. So you'll see a lot more specialization. But you're not going to, it's basically if the number of transistors that you can fit on a chip becomes constant, then the only way that you can get more speed is to make more effective use of them. You can't continue getting performance either in terms of more parallelism or in terms of higher clock speed.
Right. Because physics.
Maybe for those out there that are like catching up and trying to maybe just trying to follow along to some degree, if they're not schooled in transistors and chips, can you break down what a chip is and like what the components of it are and the thresholds we've kind of gone over the years and where we're at today? Is that possible?
Sure. Yeah, we could talk about that some. I mean, if at the lowest level, people talk about transistors, and what a transistor is it's a thing that if you apply current to it, it changes the conductivity of the material. And so what that means is that if you think of it as a wire with another wire coming into it, if you put some current on that thing, then the first wire either conducts or it doesn't. And all that means is that now you have the ability, you have a switch. So you can build out more complex logic from that switch. That's the fundamental thing that enables us to build computers. And they can build that now by etching it on silicon. So they oxidize silicon. That's what all these fabs and big chip plants are doing. They etch lots of transistors onto silicon with chemical reactions. And there's different processes for doing that. And so those processes are what enable us to cram more transistors on the chip over time. It's improvements to them. And I mean, I'm not a process scientist, so I don't know a whole lot about that. But effectively, Moore's law originated when Gordon Moore in 1965 observed that process had resulted in the effective doubling of transistors every, I think, 18 months or 2 years back in 1965. He was looking at like the range from 1958 to 1965. And so that's where that comes from.
So it was a general comment that turned into law.
It's an observation. I wouldn't say that it's a law. You can't go to jail for violating Moore's law.
We call it Moore's law.
Yeah, that's right. So yeah, we call
Don't
a lot of
cross
things
Moore.
laws.
You'll go to jail.
That's right.
Yeah.
We call them laws till they get broken, and then we're like, well.
Even the way that it's usually stated, right, 18 to 24 months is fairly vague, right? And
right.
It's an observation of the cadence with which they can double the number of transistors on a chip.
Right.
And it held pretty true. Moore thought it would hold for, I think, 10 years. And it's actually held, since 1965 pretty well. So it's somewhat remarkable in that sense. So, it's more than just an observation when it holds for many, many more years than you thought it would.
And it's somewhat been co-opted. It's somewhat been co-opted and transformed into meaning general compute power doubling. And that's kind of that was the way that we were using it. And in fact, when I was looking it up a little bit here, in an Intel executive, I think in the 90s, he said that chip performance would double every 18 months, as opposed to transistor density. And that's the general context of what most programmers and technologists talk about Moore's law. It's generally computing power and not the specific thing that Moore was talking about. Yeah.
Well, because the computing power is what enables you to do more and more with your computer.
Right.
I mean, you can do many more computations. The thing gets faster. It's good. I mean, I think the main consequence of the breakdown there is that you don't get as much single thread performance as you used to. That's kind of capped out. So you're
right.
If you're using Microsoft Word or something, like you're typing or something that has to execute sequentially, is not going to go any faster. But if you can get parallelism out of your workload, then you can actually harness all the power that's on your chip. And the difference is that if you increase the clock frequency, that just means that everything on your chip is happening faster. So that's effectively free. If you had a program that ran on an older chip, it would run just the same on the newer chip, just faster. Whereas with parallelism, if you want to harness that performance, you actually have to rework your program.
Divvy it up.
And so I think that, you have to divide it up into smaller chunks, or figure out a way to do it. It might involve like changing your whole algorithm. And that's a lot harder. And not all workloads can do that. And, not all consumer workloads can do that. So it's interesting to see how this will pan out on consumer chips. Although I think, with all this machine learning stuff going on now, it's not like there's a shortage of numerically intensive things to do on your desktop machine or on your phone. Or games like have always taken advantage of things. Yeah. We could talk about GPUs some. I mean, GPUs are an interesting design point, right? Like I think in the functional programming podcast you were mentioning earlier, you guys mentioned that, people told me I was going to have thousands of cores. Where are my thousands of cores? And I think, the answer is they're in your GPU, because that's a very different workload from what your desktop CPU is doing. It's data parallel. And so, it's easy to divide up the work that you have to do for graphics rendering. And so the GPUs are basically these large parallel, they call them vector processors, because they do, lots of the same type of instruction at once. And there's, I think in a GV100 Volta, there's, I think like 5,000 cores on that thing, if you count CUDA cores. People debate whether or not you should count CUDA core as a real core, because it's definitely not the same thing as the CPU in your system. But I mean, it's 5,000 way parallel. That's true. You can do that many operations at once. Yeah.
But very specific use case, not general purpose.
Well, you brought in a new terminology though too in this conversation. You got chip, so I'm still trying to paint the picture of what this thing is, but you brought in a new term called cores. You mentioned it earlier too, but you got the chip made of silicon, and you got transistors on that. Where do cores come into play? What are cores?
Okay. So what people used to just call a chip, because you only had one core, is a core. A core is basically a microprocessor. Although even that term is kind of fuzzy these days, because you can say the microprocessor has multiple cores. I mean, you're right. There's a lot of ambiguity. I would say, okay, so let's go back to the transistors, and build it up from there. I mean, and
then we can go to the GPUs, because that's where I want to go.
Yeah. Okay. I think that's the interesting direction. So we talked about you've got transistors on the chip. You can use those to do switching. That enables you to build what they call logic gates, and you can do things like and, or, not. Basically, you're taking two signals and you're producing a result. So 1 and 1 is 1, 1 and 0 is 0, and so on. Right? That's basic logic. You can take that, and it turns out you can build anything with that. You can build if you have a NAND gate, basically a not and gate, then you can build whatever you want. And so there's lots of ways to do that, but effectively they build this whole chip out of that, and that's they're putting that logic on the die, and that implements what people recognize as a modern CPU. And so like if we're coming at this from like a high level language, I think most of the listeners here are familiar with JavaScript or Ruby, Python, or even C. Those either get interpreted or compiled into machine instructions. And effectively what you're taking all these logic gates and you're building something that fetches instructions from memory. It fetches data from memory. The instructions tell the processor to do something with that data, and then they write it back to memory. And that's pretty much how your chip works. So if you have that pipeline where you can pull instructions from memory, you can do stuff to numbers and write it back to memory, then that's effectively what a modern core, I guess, looks like. That's a processor. You can run programs on that. And so it used to be that you had one core on the chip, and that was what you did. You had one thread of execution. You would fetch an instruction, you'd do what it said, you'd write the result back to memory, and you would go on and fetch the next one and do what it said. And there's just a whole lot of optimizations that have happened over the course of processor history that led to what we have today. Chips in Spectre and Meltdown have been in the news recently. So the chips do things like speculative execution. They can say, hey, I'm not going to know whether I want to execute this stream of instructions for a little while. But while I'm waiting to figure it out, can I go and try that? And then, as we found out, you can get bugs from that. But it's also a huge performance increase. There's things like just regular out of order execution, where effectively like your chip has logic on it that looks at the instructions coming in. It figures out the dependencies between them. And it figures out which ones don't have any dependencies right now in terms of data that they need to read or results of other calculations in the instruction stream. It'll pull those and it'll execute those instructions concurrently or with other ones that don't have any dependencies. And so that's called an out of order processor, or sometimes people call it a superscalar processor because it can execute more than one instruction at once. There's vectorization. So like most chips have some, types of instructions that will do multiple things at once. So if you know that you have, 4 numbers lined up in memory and you want to multiply them all by 2, you can pull them all in at once and do those operations all at once if they're the same. And so there's lots of these different sequential optimizations that people have done, and that's what goes into your one chip. And so now that you have all of these extra transistors, because you can increase the clock speed on the one chip or on the one core, people are building out the number of cores that they have on a chip. And so they basically just, they have the same core. They're not trying to cram too much into that one core and increasing the power density to the point that it would cause problems, but they're just scaling that out with the number of transistors. Does that make sense?
Totally.
It's still, when you sit back and think about it, it's still mind-numbingly awesome what we can actually build out of those core primitives. Like just where we've gotten from where it starts, you take it for granted. You don't think about it much, but when you do, you sit back and think about it, all ones and zeros and logic gates at the bottom of it all. What we actually can create out of that has been amazing.
That's true.
Oh, there's tons of layers. And I mean, if you think about it, that people started out just programming to the chip, right? Like if you got a new machine, back, say in the founding days of this laboratory, 1952, you would read the manual and, the instructions that the way that the programmer manual had assembly code in it. It said, here's the instructions you can execute on this chip. This is what it can do. And you'd have to actually, think about memory and, what, how you're, managing it, what you're pulling into the core, how much memory you have, and things like that. And now, you don't even think about that. You can instantiate things dynamically. You don't have to think very much about memory in most of the modern languages, and it's a pretty nice ecosystem. I mean, I think, the reason that the multi-core stuff doesn't, I think, change your perception of what's going on the computer quite as much, or at least from a programming perspective, is that, one reason is that there are a lot of multi-threaded programs, and even your operating system is, even before you had multi-core chips, your operating system was executing multiple things at the same time. It was just doing it by time sharing. And so what a context switch is. It's when you're executing one program and then the OS says, oh well, there's this other thing that's running at the same time. I'm going to swap that in, execute it for a little bit, then I'm going to preempt it and switch back to the other thing that you were doing. And effectively, that's how your OS did multitasking. Before you had multi-core chips, is by just splitting up by switching back and forth between different tasks really rapidly. And now, you're on your chip, you really can have things executing actually in parallel. And so it's to some extent, it's kind of a natural transition, right? Because you can just execute different threads on different cores. And the operating system has to manage that. But you still have context switching too. So, you can still execute many more tasks on your chip than you have cores.
This episode is brought to you by DigitalOcean. DigitalOcean recently announced new, highly competitive droplet pricing on their standard plans on both the high and the low end scale of their pricing. They introduced a new flexible $15 plan where you can mix and match resources like RAM and the number of CPUs, and they're now leading the pack on CPU optimized droplets, which are ideal for data analysis or CI pipelines, and they're also working on per second billing. Here's a quote from their recent blog post on the new droplet plans. Quote, "We understand that price to performance ratios are of the utmost consideration when you're choosing a hosting provider, and we're committed to being a price to performance leader in the market. As we continue to find ways to optimize our infrastructure, we plan to pass those savings on to you, our customers." End quote. Head to do.co/changelog to get started. New accounts get $100 of hosting credit to use in your first 60 days. Once again, head to do.co/changelog.
Well, Moore's Law is not dead, but dying. Murphy's Law, however, eternally true. Do you guys know Murphy's Law?
Still true. Yes.
Will always be true. Adam, you know that one?
Yes.
Murphy's Law?
Yeah, that's a real law.
Yes. Anything that can go wrong will go wrong.
So
Eternally true.
I guess if you want to get back to the Moore's Law dying aspect, I think GPUs are a good example of one way that you can take more effective advantage of some transistors and sort of combat that power law or the Dennard scaling problem. The GPUs are in terms of the number of operations you can do on them, you get a lot more performance per watt if you can exploit them than you do out of a CPU. So if you have a workload that's data parallel, you can pose it that way, then you can execute it more efficiently on a GPU than you can on the CPU. And so that's and you have like 5,000 cores on there, right? It's a big scale out machine. It's doing vector stuff. It's very power efficient, and that's one way to use the transistors more effectively for certain workloads than for the CPU. And I think that's where you're going. You're going to see other types of technologies take over that are better at certain tasks. I think in our community, the other places that people are looking so there's quantum computing. People talk about that a lot.
I want to talk about that.
Yeah. Okay.
Put that on the sideline.
I can't say too much about it.
Okay.
Not an expert, but I mean, there's like a whole beyond Moore's Law thrust in DOE, and I think in the broader CS research, funding agencies.
Mm-hmm.
What's the DOE?
The Department of Energy.
Okay, just to be clear, for those not in the U.S. and hearing acronyms to know what they're talking about.
Yeah, we could do we didn't do the origin story thing at the beginning, which we could do.
You can go listen to RFC. I think there's some in that show to some degree about where you work and what you do, and so I'm pretty sure that's how Nadia opened it up.
Right.
Yeah, that's true. So we could talk about the DOE some later. DOE is where I work. I work at Lawrence Livermore National Laboratory, and we care about high performance computing. So yeah, quantum computing is one way that you can use a different type of technology to do computation. So far, people haven't really, they've shown that it's useful for certain problems. So like there's a D-Wave system. Los Alamos has a D-Wave system that they're looking at. It's a type of quantum computer that can do something called quantum annealing, which allows you to solve certain optimization problems very fast. But again, that's a different model of computation. It's not like a script. It's another type of thing. So if you have to do optimization problems, that's a good thing to use, and you can do it really fast. There's something called cognitive computing that we're looking at. So at Livermore, we have a partnership with IBM where we're looking at their True North architecture, and they call it a cognitive computer. Effectively, what it is it's a chip that you can basically put a neural network on, and you can evaluate it very quickly. And so it's good for machine learning workloads. If you need to do some machine learning evaluation along with your workload, where I'm distinguishing between like training and evaluation, then you could potentially do it faster with the True North chip. And then, to some extent, there are limitations to how you can do that. You have to discretize the neural net a certain way so that it fits on the chip. and you can only do certain types of neural nets. But you can pose a lot of different neural net problems that way. So we think it could be useful for helping to accelerate some of the simulations that we're doing, or to help to solve problems that are really hard for humans to optimize at runtime. So that's another model.
Are there private sector equivalents, Todd, to these things that you're speaking of, or are these the kinds of things that you only find in the public sector in terms of the cognitive learning machines? So
I believe True North is available, and you could buy it if you were in the private sector. It's an IBM product. I'm not 100% clear on whether it's just a research prototype that we're dealing with, or whether you can actually buy with these and play with them in industry. But I mean, I know that I think some industry players have D-Wave machines, so they're playing with those. So you can get them, play around with them. I definitely think that it's still in the research phases in terms of what you would actually do with it.
Yeah.
The True North chip is interesting because it's a little closer in terms of actually deploying those, because the people do have machine learning workloads, right? If they want to accelerate them, they could use something like this to do that. What it doesn't accelerate is the training. So you would still have these giant batch jobs to go and analyze data sets to build the neural net that you use to either to classify or to analyze the data once you're done training that thing. But I mean, I think the theme across all these different areas is that it's more specialization and
special purpose.
Yeah.
Huh. So tell us real quick. So you mentioned you work at Lawrence Livermore National Lab.
Yes.
So you have these specific use, and you said we care about high performance computing. Maybe explain the specific use cases. As much as is public knowledge, or not top secret stuff that you guys do, and you're applying these technologies to.
Okay, so I work for the Department of Energy. I think Department of Energy has been in the news as Trump has picked his cabinet lately. It's the part of we deal with a couple of different things. I think the DOE is the biggest funder of science research in the U.S. alongside the NSF, and that involves funding universities. It involves funding the national laboratories, and we're also in charge of managing the U.S. nuclear stockpile and making sure that it stays safe and reliable. And so across all of those different scientific domains, there's a whole lot of physics simulation that needs to get done. And effectively, we are using simulation to look at things that you either, can't design an experiment for, or that it's too expensive to design an experiment for, or that it would just be unsafe to design an experiment for, or that you shouldn't design an experiment for. And I guess on the NNSA side, so Lawrence Livermore is part of the National Nuclear Security Administration, which is under the DOE.
Okay.
The unsafe thing that we're looking at is how do nuclear weapons work? And so that's a lot of the simulation workload that takes place here. We also do other types of simulation like climate science. We have a lot of people working on that. We look at fundamental material science, all of these big either computational fluid dynamics or astrophysical simulations, geological simulations, earthquake simulations, all these physical phenomena. We have simulations at various degrees of resolution that we can look at to figure out what would happen if. So like we have some guys who've done predictions about earthquakes in the Bay Area. Where would the damage be? We look at, will this weapon continue to work? We also do things like detection. Like if you had something like this type of device and someone was trying to ship it in a container, how might you figure out that it was there without opening every container? There are lots of things like that that the DOE looks into, and high performance computing drives all sorts of different aspects of that. Yeah. So, and I guess the other interesting facility here that's in the news frequently is the National Ignition Facility, which is a nuclear fusion experiment. So we're trying to make a little star in a big, building the size of 3 football fields, where we've got like 192 lasers that fire at this little target. And so simulating how the lasers interact with the target, how they deposit energy there, is one of the things that we can simulate on the machines here.
You're building a star inside of a big building.
A little tiny star. Like
Oh, tiny.
Very,
Well, to me, every star is big, I guess. So a tiny star relative to other stars, but a big building.
Well, let me be clear. It's a star in the sense that we're trying to get fusion burn to happen.
Right. I was going to ask you, what exactly is a star then?
I was just waiting for Adam to hop in because this is like where he gets super excited. His ears are perking up.
Well, I was still stuck back at the size of this True North. And I was thinking like the size of the thing. And I was actually thinking about at what point because these things are really, really small. At what point does a, chip or a microchip or however you want to term this, get so small that it gets to the very, very small, which if you study physics and things like that, life like we see it, then you see the very, very big, which is planet sizes and, universe sizes. Then you get the very, very small, which is like atom sizes. Like how small do these things get? But then this star conversation is far more interesting to me.
Oh,
I like that.
So there's lots of physics that goes on in the Department of Energy. So I guess I would, shameless plug, I can endorse the Department of Energy. It's a good place to work because you get to find out about stuff like this.
Sounds interesting.
And so, So, I mean, the interesting thing about NIF is that's the National Ignition Facility, is that you're simulating a star. It's very small. It's the target is like a few millimeters in diameter versus, but you're trying to cause the same kind of fusion burn that would happen in like the sun.
And so it's all these lasers colliding, right? The light from these lasers colliding, they create the fusion burn.
That's right. The lasers come in, they hit this kind of cylindrical thing called a horam. It's made of gold. That gets really hot. X-rays come out of it and implode the target in the middle. And that's the idea.
Are you doing that a lot, or are you simulating it on computers and then doing it very few times?
He's saying they can do it physically in this big building, but then these chips that he's talking about, they can do it simulated.
This is a good example of the type of work we do. So NIF is where you're trying to do it physically. We're trying to get fusion burn there, but to understand how this thing is working, right? We have to do simulation to prototype the designs, and I think we do about 400 real shots in a year over at NIF, where we actually turn the lasers on, point them at a target.
Well, that's not too many.
Yeah, it's and we're ramping that up. It's a scientific facility, so you can do research for lots of different groups. Yeah. In conjunction with that, we do simulations to see if what we're simulating matches what really happened, right? And that's an iterative process. So you do more simulations. You say, okay, it matches. How do I change the design to do better, to get more energy out? And then you go simulate that. It says it's going to do better. You try it. Maybe it doesn't. And then you iterate on that until the two match. And ideally, that's the process that we use for designing these things. So that's where the HPC comes in, is simulating something like that takes an awful lot of compute cycles. So like I work in Livermore Computing, which is it's a compute center, kind of like a data center, but we have machines that are dedicated to doing computation instead of persistent services like a data center would have. And we have, I think, over 2 million cores just in this building for all of our computing needs, and we have some of the largest machines in the world here that people run these parallel applications on.
2 million cores, huh? That's a lot of cores.
We have one machine with 1.5 million. Which is number 4, I think, in the world now.
Wow.
So that's Sequoia, and we're installing the new machine right now. It's called Sierra. It's a big IBM system. It's with Power 9 processors and NVIDIA GPUs.
This is highly specialized equipment for highly specialized tasks.
Yeah, that's true. I'd say that you buy a different kind of machine for HPC than you do for like the cloud. But some aspects of running a data center and a compute center are very similar, like managing power, temperature, stuff like that.
Security.
I would say that the security, exactly. That's important. We've been rolling out meltdown patches all across the facility.
I was just gonna ask that.
Yeah. And the interesting thing, so we see performance hits from that, so we try to optimize that.
How big are the performance hits that you're seeing? There are some reports to be up to 30%, but doesn't sound like that's necessarily the case.
In line, depending on the workload. I think it really depends on what application you're running, because it's that system call overhead that you're paying for. So we have an interest in high performance computing because there's basically never an end to the computing capacity that we need to simulate the stuff that we're looking into. And so, most of the place where we get into architecture around here is in optimizing the performance of applications. So, we have people who work with the application teams and they say, okay, your simulation does this. How do I, how can I make that execute more efficiently on the hardware? And then we also look at procurement. So we're like, we have this workload. We know that we need to run these things. So what's the next machine that we're going to buy? And so, that I was talking about Sequoia. Sequoia is the, 16 realized 20 peak petaflop machine that we have on the floor right now. Our next machine is going to be a 125 petaflop machine. And so the whole procurement process, people get together and they look at the architectures from different vendors and they say, how is our workload going to execute on this? And so I think, in the future, you're going to have to think more and more about matching the applications to the architecture. And we had to think about that because our next machine is a big GPU system. So, here's an example that probably gets at kind of the heart of this Moore's Law stuff. Sequoia is the previous generation machine. It's about 100,000 nodes. Each node has a multi-core chip on it. And they're all PowerPC chips. And so, our workloads could execute pretty effectively on that. And it was fairly easy to scale things out to a large number of processors. The GPUs have kind of won in terms of that's the thing that has a market out there for games and for other applications. And so, we have to ride along with the much bigger market for commodity computing. And so our current machine is only 4,000 nodes. It's got Power 9 processors on them, and it's got 4 GPUs per node. And so that's, in terms of number of nodes, it's a much smaller machine than Sequoia, but it's way faster. And it had, it's 125 petaflops versus 20. And so that's where, the GPUs will win. But for us, that's a big shift because we haven't used GPUs as extensively before. And so now we have to take our applications and port them so they can actually use the 4 GPUs per node. And that's a challenge.
Give us an idea of what range we're looking at here. US dollars.
For the big machines?
The big machines. Are we talking like hundreds of thousands of dollars, but millions of dollars, tens of millions? What's the order of magnitude?
So for most of the big machines, like if you're going to get a number one on the top 500 list, which is like the place where they have the list of the top supercomputers, is probably like has been $200 million at least in the DOE for the system, and that's procured over the course of like 5 years. We start 5 years out. We talk to vendors and we get them to pitch. They write a proposal that says, here's how we could meet your specs. And then we have a big meeting where we go and we look at, how they project this will work on our workloads. They do experiments with some of our like applications. And we also look at the other specs on the machine and different parameters, how much memory is it going to have? How much memory per node? How many nodes are we going to have to use GPUs? Are we going to have to use like Intel Xeon Phi chips or other things? And then we pick the one that we think will best meet our needs going forward.
How would you like to close that deal, Adam? $200 million.
That's a lot of money.
Be the salesman on the front end of that thing.
Yeah, that's a long sales process.
You go out to dinner after you make that sale.
Yeah.
And if you want the details on our current machine, there's a nice article at Next Platform by our CTO who is in charge of that procurement process.
Awesome. Well, we'll make sure we link it up in the show notes.
All right, Todd, I have a suggested project for you for the NIF folks. After you guys finish that star you're working on,
I'm sure they'll listen to
next project. Yes. Sharks with laser beams on their heads.
I feel like people have come up with that idea before.
Just for your consideration. Well, simulate that a few times. I think you'll wind up with it.
Are you sure no one else is working on it?
Well, I think you'd be bleeding edge.
All right. With simulation, we can make it better. We can make more effective sharks with laser beams. That sounds scary, though. I think we should think about the consequences of doing that.
Looking to learn more about the cloud or Google Cloud Platform?
But you don't know where to begin?
Check out the Google Cloud Platform weekly podcast at gcppodcast.com, where Google developer advocates Melanie Warwick
Hello.
and myself, Mark Mandel, answer questions, get in the weeds, and talk to GCP teams, customers, and partners about best practices from security to machine learning, Kubernetes, open source, and more.
Listen to gcppodcast.com and learn what's new in cloud in about 30 minutes a week.
Hear from technologists all across Google, like Vince Cerf, Peter Norvig, and Dr. Feifei Li, all about lessons learned, trends, and cool things happening with our technology.
Every week, gcppodcast.com takes questions submitted by our audience, and we'll answer them live on the podcast.
Subscribe to the podcast at gcppodcast.com, follow us on Twitter at gcppodcast, or search for Google Cloud Platform Podcast on your favorite podcast app.
And by GoCD. GoCD is an open source continuous delivery server built by ThoughtWorks. GoCD provides continuous delivery out of the box with its built-in pipelines, advanced traceability, and value stream visualization. With GoCD, you can easily model, orchestrate, and visualize complex workflows from end to end. It supports modern infrastructure with elastic, on-demand agents and cloud deployments, and their plugin ecosystem ensures GoCD will work well in your unique environment. To learn more about GoCD, visit gocd.org/changelog. It's free to use and has professional support for enterprise add-ons available from ThoughtWorks. Once again, gocd.org/changelog. So I guess the question I have is, like, if you've got this $200 million computer, right, it's got to be something that's pretty demanding, right? People are going to want to use this thing because you're not going to want to not get the return on investment for that thing. So, like, what's it like scheduling, managing a project that's on it? How do you schedule time for it? Do you have to predict how long your project will take, the compute time? Like, give us a day-to-day operation of using one of these computers.
Okay, so I mean, I can't speak necessarily to what the actual application guys would do, because I'm not I'm a performance guy, so I work with them to help speed things up. But I mean, the usage model is basically you have to write a proposal to get time on these things. For the bulk of our workload, and this is the case for other Department of Energy laboratories too. You have to write something up that says, I have this scientific problem. It really needs a lot of CPU cycles. It's not possible without that. And here's what it would enable. This is why it's worth, the time on the machines. And so those go through, here and at Argonne and at Oak Ridge, all these other labs, a competitive process where reviewers look at the proposals, they evaluate, does it have merit? And then once that's done, you get assigned hours according to what you asked for on the machine. So you get CPU hours. That's millions of CPU hours or more, depending on what the project is. And a CPU hour is measured in terms, I think we may be doing node hours now. I'm not sure if it's CPU hours or node hours, but basically it's just a measure of how much compute power you're allowed to use. So that's how we justify it. And the machines stay busy all the time because we have science projects that need them for their workloads. We have more work than the computers could ever possibly do, but they are doing it fast, so it enables new science. So I think in a given day at the lab, there's a bunch of users. We have 3,000 users for the facility. Some here, some are collaborators, some are at universities that we collaborate with. They're running jobs, applications. It's like a big batch system. You log into it, you say, here's the job I want to run, here's how many CPUs it needs, or how many nodes it needs, and here's how much time it needs to do that approximately. And then we have a scheduler that just goes and farms those jobs out to the system. And so the people at the compute center, we look at what's going on. We try to manage the scheduler so that it has a good policy for all these different users. And we have performance teams who, help the application teams actually optimize their code to run on the machine. And that's an iterative process, right? So for a machine like the new Sierra machine I was talking about, we'll typically have a smaller machine in advance of that that's similar. We have a Power 8 GPU system instead of a Power 9 GPU system that we've been testing on, and they'll get their code running on that in preparation for the new system. And in that process, we'll look at we'll run profilers on the code. We will look at traces to see if it's communicating effectively between all the nodes. And we'll help out the application teams by saying, you should modify this, or we need to change this algorithm. I think one of the things that we've been helping people with a lot lately, and especially with the GPUs and also with other centers using more exotic chips like Xeon Phi, which is like an Intel many-core chip. It's like a 64-core Intel chip. We need the same code to execute well on all these different architectures, and that's not an easy process. So if you have a numerically intensive code, you write it one way, it might execute well on the CPU, but not on the GPU. And we'd ideally like to have one code that the application developers maintain, and have that have essentially some other layer handle the mapping of that down to the architecture. So one of the things we've developed is we call them performance portability frameworks. So we have this thing called Raja. It's a C++ library where you can write a loop. Instead of a for loop, you write a for all, you pass a lambda to it, and you pass that for all a template parameter that says, hey, I want you to execute on the GPU, or I want you to execute on the CPU. And that allows them to tune effectively for different architectures. They can kind of swap out the parallelism model under there. And so, tuning that, getting the compilers to optimize it well for different machines, that's the kind of thing the performance folks have been working on.
So you answered the one question that I was thinking when you talked about scheduling is, do these things ever sit idle? Because that would be like the worst use of a huge, massively powerful, expensive computer is idle time, right? So I guess it's heartening to find out that there's so much work to do that's not a problem whatsoever. In fact, the problem's the opposite, is that you need to start procuring some more to continue, more and more research.
The other side too, it sounds like you do a dashboard or something like that. Do you ever see the computer? Do you actually get next to it, or do you just operate whatever you need to do through some sort of like portal or something like that?
I mean, we have people who get next to the machine, and we give tours of the facility to folks who visit the lab sometimes.
But you don't have to put your USB stick into it to put your program on it and run it, right? You're
no,
okay.
Punch cards.
Okay.
Yeah, no. So basically, I mean, these things look like servers, like you'd be used to, right? Like you have a desktop machine, you SSH into the computer, and then there's a resource manager running on it. So like Slurm is the open source resource manager that we use. It's developed here, and now it's got a company, SkedMD, around it. And the users would say, sbatch command line, and then they would take that command line, put it in the queue, and then eventually run it on however many nodes they asked for, or srun if they want to do it interactively and wait for some nodes to be available. And the wait times can get pretty big if the queues are deep. So yeah.
So you get assigned hours, but you don't get assigned 9 in the morning to 10 in the morning. You get just hours, and you're in a queue. Whenever your queue comes up, you execute.
Right. You get a bank that comes with your project. We call it a bank. That's how many total CPU hours you have. If you submit a job, then when you submit it, you have to say, here's how long I expect it to run for, and the scheduler will kill it after that much time. And then you see the nodes you want, and then it runs for that long. And however, the length of time it runs times the number of nodes it used, times the number of CPUs per node is how much they subtract from your bank at the end of that. And so effectively, you get a few, multi-million CPU hour allocation. You can run that out pretty quickly if you run, giant jobs that run for a long time.
So Todd, I first met you at the Sustain event last spring, almost summertime, I suppose, at GitHub headquarters. You were very involved in that. And in fact, that's when you hopped into our Slack for the first time and helped bring some people from the lab to that event. And so you have this interest and passion around sustaining open source, because that's why you were there and involved. And we appreciated your help. But tell us in the audience the intersection of where open source comes in with the work you're doing with the supercomputers and the lab work.
Sure. So I'd say two places, and they're big places. I think for our computer center, the folks who run it, we prefer open source for nearly everything. For the resource manager, for the file systems, we have big parallel file systems like Lustre. For even the compilers that we use, we're investing in Clang or in LLVM to create a new Flang to do Fortran for some of our codes. And so I would say that the majority of what we do at the compute center is open source in terms of the infrastructure that we're using. Our machines run Linux, and we have a team downstairs that manages a distribution for HPC. We call it TOS, which is a Trilab open source stack. That's basically a Linux distribution with our custom packages on top of it, and that's how we manage our deployment for the machines. So that's one way. And then we have people working on, the people who work on those projects, or like ZFS, is used in Lustre. We have a guy who actually did the ZFS on Linux port and manages that community. And I think we get a lot out of that. It's Brian Bellendorf at Livermore, not the Brian Bellendorf who's doing blockchain stuff, but actually another Brian Bellendorf, the same name. Yeah, there's two Brian Bellendorfs in open source.
Wow, same spelling and everything.
Yeah, everything. Wow. Yeah, he said that they met once and talked to each other.
That is confusing. We just had the other Brian Bellendorf on the show. We interviewed him at OSCON last year about
listen to that
Hyperledger. Yeah.
Yes. Yeah. So this is ZFS. So there's the ZFS Brian Bellendorf and there's the Hyperledger Brian Bellendorf.
Okay.
One of them is in the building with me. Yep. We were talking about how we procure these big machines, and there's a contract associated with that. In that we allocate some time for the vendor to contribute to open source software. We require that as part of the contract. And so they work with us, and they make sure that our software and other software that we care about from the DOE and elsewhere actually works on the machine. So that's another way we interface with the open source community.
On that note, then, it sounds like you're pretty intimate in terms of like what involved in like the process or what's on these machines. Do you have good relationships with those who sysadmin these machines? Or do you as a collective, are you able to say, well, we prefer this flavor of Linux? And it seems like since you choose open source, you have some sort of feedback loop into like preferences that everyone can put on this machine and do all these fun things you do.
Yeah. So at this center, I mean, there's a software development group, there's the system administration group. They're all in the building that I'm in, which is attached to the compute center. There's a lot of crosstalk between those different areas, and then we also talk to the researchers, right? Who run applications on the machines. I would say that Livermore Computing, at least like on the infrastructure side, is definitely involved in choosing what open source we want to run on the machines and when we maybe don't want to go open source. Like we run proprietary compilers because they're fast, for example. Right. But we also do things like invest in the open source compilers to try to say we want an open source alternative so that we have something that we can run on the machine that will work and work well.
The reason I asked that is because it seems like the application process is very protected to manage the load on those machines and the time. And so I just wondered if, the involvement of what's on the machines and who manages them and what's, all that stuff is just as protected. If seems like one side's a little bit more loose, but to get the time, it's a big ceremony, a big process, and, could be gatekept to some degree.
Yeah, I guess I would say that like HPC, I mean, it's a research computing field, right? It's mostly researchers who need this much compute power. And so the calls for proposals are not unlike the calls for funding that people put out for academia. There are open ones, and so like the Office of Science Labs have the Insight program, where you can apply for time on Oak Ridge and Argonne's machines, which are similarly large, if not. Oak Ridge has a larger machine than ours right now. And for us, our customers are slightly different because we work with Los Alamos National Lab and Sandia National Lab. And so our proposal processes, at least on like the classified side, are mostly between those labs because they're about the weapons program and stuff like that. But then there's, there are other places where you can get time for basic science runs. So like when we get a new machine like Sierra, we put it out there and we let, early code teams, like the guys who maybe have like an important science application that isn't as complicated as maybe some of our production codes, who can get on there early and, show off the machine. We let them run. There's a few months at the beginning where we let them use the time with allocations there. So I guess I'd say there's a lot of different ways to get time on the machines, and it's pretty low overhead. It's not quite like writing a full academic proposal. It's pretty open.
And we're on this open source kick. I was just curious how that flavored in, because as you're describing your choices and and I guess the primary choice of choosing open source, and that's your preference, it seemed like while there's a lot of process around the proposal flow, maybe there's a little bit more crosstalk, as you mentioned, at like involvement with other teams that have access to these super expensive machines. Like that's a huge privilege, because like I don't have access to a $200 million machine. I can barely afford one that costs $7 million, and I gotta like borrow money from grandma or something like that, So
7 what? 7 million?
Thousand.
Oh. You said 200 million, and then you said you could barely afford one that costs 7.
I assumed everybody thought that was in the thousands. Like
I assumed the denominator was saying the same.
Grandma ain't got millions, man. You can quote me on that.
Same question.
I guess what we're trying to say is, Todd, is how can we get some time on this computer?
Yeah. We've got some research.
You have to have so I guess if I had to boil it down to something, you have to have justification for getting on the machine. You have to be able to show that you can make scientific progress with your hours. So that's what the process is about. But I guess
sharks and lasers, man.
Sharks with freaking laser beams on their heads. I told you my justification already.
Ill-tempered sea bass.
Oh boy.
Yeah.
I guess the other elephant in the room, Todd, for justifications, and you addressed this to us in the break, but please, for the audience sake, because I know we probably have a fair amount of Bitcoin miners listening. And so I think that is the other thing that has people kind of, putting their pinky up to their mouth.
CPU time.
Mm-hmm.
Yeah.
Yeah. What about Bitcoin mining on these rigs?
Okay, so we're not allowed to mine Bitcoin on these machines. It's not legal to use government machines to mine for Bitcoins. But even if you did, it wouldn't be worth it. If you look at what people are using for Bitcoin mining, a lot of that is like custom chips. They're very low power and only do hashing. So you'll do way better investing in that than you will in one of our machines. So, and I think at some other compute center, people have been fired for trying to mine Bitcoin on the machines. Yeah.
Wow.
Yeah. You can Google for news stories about that. But I guess I want to be a little clear about on the openness front. So, the application for time is separate from the software that you actually run on the machine, right? So, like we have a lot of open source projects that live for much longer than any allocation or any machine, really. And there are a lot of people who work on those, and those are open. Some of them, you can even run on your laptop, and scientists do. So like a lot of development for these machines does happen on people's laptops, and then they scale the program up to run on the big machine. So, there's a lot of open source software development that happens, even if the process for getting access to a big machine isn't open, and you can run that open source software on, the machine that you do have for, $7K
or
less.
$7K.
Yes.
Your grandma could run that, Adam.
That's right. Grammys can run that.
So what about the open source community? Seems like anytime when I think of a government operation, you think, especially with the security constraints and a lot of the quote unquote red tape, seems like actually deep involvement with a community that's built on openness and freedom and all these things that are kind of opposite of like secrecy and closed. Is there any give or take there, or is there red tape? Are there issues around that, or has it all been pretty easy in terms of integrating your open source work into the greater open source community?
So I'd say that historically Livermore is pretty good about open source. I mean, we started using Linux clusters like in the late 90s, and we've been working on the operating system for that. We've developed like Slurm, the resource manager, has been open source for a long time. So putting stuff out there has not been such a problem. There is a release process that you have to go through that's kind of cumbersome, but once you do it, like we did for SPAC, the package manager I work on, you can work out in the open on that as long as you stay within a certain project scope. And so I mean, there is some red tape around that. Obviously, we don't want to release some of the things that we develop. But then again, we use a lot of open source internally and benefit from the broader open source community. So I would say that DOE has a pretty active open source development ecosystem, and we leverage things that are developed by other labs, and other labs develop or leverage things that are developed by us. And I think there's a lot of back and forth. I would say that like the interaction model on the projects is maybe not quite the same as like a large infrastructure project, like, I don't know, like Kubernetes or Docker or something like that, just because, I mean, it's scientific computing. So people get funded to solve a particular problem, not to develop software. So there are, sustainability issues around how much software development time can we actually put on this project. On the production side, though, the facilities, I mean, their job is to keep the center running and to do it efficiently. So I think that's why you see a lot of open source coming out of there. But then again, there are long-lived research projects that are very widely used. So like one good example of that is in like the math library community. So for large-scale parallel solvers, the different labs have teams working on that stuff, and there are some solver libraries like Livermore has Hyper, Sandia has Trilinos, and Berkeley Lab has some solvers, and also things like finite element frameworks, things for meshing and for building these big models of physical systems. So like Livermore has a library called MFEM that has a big open source community around it, or well, not big by JavaScript standards, but big by scientific computing standards.
Right.
Yeah. So some of them operate like communities, I would say, and then others kind of tend to, stay within a particular group, or, they maybe don't have a cross lab community. It just depends on the software and what the funding and the interaction model has been historically. I do think like more community could help a lot of projects if people started thinking more in terms of like, how do I sustain this over time? How do I get more contributors? I don't necessarily think that we build research software with growing contributors in mind.
Well, I think it's interesting that you got the three I took note of earlier. The one you obviously talked about on Request for Commits back. That's the project you work on primarily.
Yes.
Then you've got Slurm, which I think is a workload manager, if I got you correctly. That's actually what you interface with to put your projects onto a supercomputer. Is that right?
Yeah, it runs the jobs.
It runs the jobs.
Does the scheduling. Yeah.
Then you got Luster, which I was just noticing down in the trademark is a Seagate Technology trademark. So that means that that's the file system. So these things are important enough for you to have open source projects alongside them that I guess are, more specific to, say, a supercomputer scenario versus, say, a laptop scenario.
Yeah, for sure. I mean, we have to pay for open source development for like a parallel file system that'll run fast on our machine. We have to keep the computers working. So
right.
A lot of the infrastructure projects are aimed at that.
Seems like some of this stuff should come with a $200 million computer.
Well, so
I mean, I'm just thinking like.
Yeah.
So it does to some extent. Like, so
did you get a T-shirt or anything?
We haven't gotten
Bring
T-shirts. You do get a mural.
Okay?
You can get a mural painted on the side of the machine. So like if you look at like the NERSC machines, like they have a picture of Grace Hopper painted on the side of their machine. Cool. But so there is a lot of software that comes from the vendor. So like Cray provides a whole programming environment with their system. It's not necessarily open in the same sense. If you buy an IBM system, they will bundle like their file system, which is GPFS. It's a competitor for Luster. It's proprietary. And which one you go with depends on what value do you get out of the procurement.
Right.
Which one do you think is going to perform better? I'd say performance drives a lot of the decisions at the procurement level. But openness is also a big factor.
Does it come with hard drives?
Yeah. So the system would come with, a parallel file system, right? So it's not just hard drives. It's like racks and racks and racks of hard drives.
Right. I was gonna make a joke to say like, when you get it, do you just wipe the drives and put your own stuff on it like you do any old? Do you do it at scale essentially? Like when I get a machine, even a Mac, I sometimes will just wipe it and put a brand new version of OS 10 on there, or Mac OS now because I just like it. I just do that, my own way.
So yes, we do that effectively with our Linux clusters. So
Gotcha.
we build our own distribution, like I was saying, and so we have a TOS image that we run across those. For the bigger machines, so for what we call our advanced technology machines that are in these large procurement packages, it's much more vendor driven in this because it's bleeding edge. So we rely a lot more on the vendor to provide the software stack. Although, our the next machine is going to be Linux, so it's the machines for the OS at least run Linux.
Which flavor of Linux?
We run across the center here. We run RHEL. So that's the distro that typically is at the base of our TOS distribution, and then some machines run SUSE, but not at Livermore. Like the Cray machines, I think use SUSE as their base distro. They also build their own kind of custom lightweight versions of Linux for the actual compute nodes. They want to reduce system noise, so they don't want a lot of context switching going on and stuff that would slow down the application.
When you say RHEL, that's RHEL, right?
Yeah, a Red Hat Enterprise Linux.
Gotcha.
Yeah.
Cool. This is pretty interesting to kind of peel back the layers of a supercomputing research laboratory like this, and see how open source fits in, how $200 million, what it buys, how you procure time, how you propose time, how you interface with other teams that manage open source software, how you determine preferences, and this is an interesting conversation that's not exactly the typical episode of the changelog. So hopefully, listeners, you really enjoyed this, and if you did, there's a way you can tell us. You can either hop in GitHub, so github.com/thechangelog/ping, or join the community. Go to changelog.com/members. What is it? No, it's community/community. Sorry.
Mm-hmm.
Go there, which is what Todd did one day, and he's like, "Hey, y'all are doing this conference called Sustain. I'm gonna go, and I want to bring some friends." And wow, this is an awesome community. So maybe Todd, to close this out, what can you say about hanging out in Slack?
Hanging out in Slack
With us.
With
Slacking with us.
changelog. So I do that because it's nice to be in touch with I guess a different open source community, right? So I think the changelog is kind of heavy on web development. I used to be a web developer before I came to DOE, so I like to keep up with that stuff and see what's going on out in the cloud, as well as over here in the DOE. So it's been a nice time.
Well, Todd, thank you for coming on the show today, man. We're huge fans of yours, and just thanks so much for schooling us on Moore's Law. Appreciate it.
Cool.
All right, that's it for this show. Thank you for tuning in. If you haven't been to changelog.com in a while, go there, check it out. We just launched a brand new version of the site. Go to changelog.com and subscribe to get the latest news and podcasts for developers. Get that in your inbox every single week. We make it super easy to keep up with developer news that matters. I want to thank our sponsors, Rollbar, DigitalOcean, GCP Podcast, and GoCD. And bandwidth for changelog is provided by Fastly. So head to fastly.com to learn more. Error monitoring is by Rollbar. Check them out at rollbar.com. And we host everything we do on Linode cloud servers. Head to linode.com/changelog. Check them out. Support this show. The Changelog is hosted by myself, Adam Stakoviak, and Jared Santo. Editing is by Jonathan Youngblood. Music is by Breakmaster Cylinder. And you can find more shows just like this at changelog.com or wherever you subscribe to podcasts. See you next week.